All right. Okay. So we're doing some cool stuff. So I'm going to first read this intro. All right. Spotted owls. In 1990, the northern spotted owl became the center of a nationwide controversy over the use and misuse of the majestic forests in the PNW. Environmentalists convinced the federal government that the owl was threatened with extinction if logging continued in the old growth forests where owls prefer to live. The timber industry, anticipating the loss of 30 to 100,000 jobs as a result of new government restrictions on logging, argued that the owl should not be classified as a threatened species and cited a number of published scientific reports to support its case. The population of spotted owls continues to decline, and it remains a species caught in the crossfire between economic opportunities and conservation efforts. Mathematical ecologists help to analyze the effects on the spotted owl population of factors such as logging techniques, wildfires, and competition for habitat with the invasive barred owl. The life cycle of a spotted owl divides naturally into 3 stages. The owls mate for life during the subadult and adult stages, begin to breed as adults, and they live up to 20 years. Each owl requires about 1,000 hectares for its own home territory. A critical time in the life cycle is when the juveniles leave the nest. To survive and become a subadult, a juvenile must successfully find a new home range, and usually a mate. The first step in studying the population dynamics is to model the population at yearly intervals. Usually one assumes that there is a ratio of 1:1 females to males in each life stage and counts only the females. Its population at year K can be described by a vector. What is this? This is juvenile, subadult, adult. Using actual field data, Using actual field data from demographic studies are the stage matrix model. Here, the number of new juvenile females in year K plus 1 is 0.33 times the number of adult females based on the birth rate. 18% of juveniles survive to become subadults, and 71% of subadults and 94% of adults survive to be counted as adults. The stage matrix model is a difference equation. Such an equation is often called a dynamical system or a discrete linear dynamical system. Yeah, that's what I would call it. Discrete linear dynamical system. Because it describes the changes in the system as time passes. The 18% juvenile survival rate, is the entry affected most by the amount of old growth force available. Actually, 60% of the juveniles normally survive to leave the nest. But in Willow Creek, only 30% that left the nest were able to find new home ranges. The rest perished during the search process. Wow, that's crazy. Section 5.6 will show that the model described in the chapter introduction predicts the eventual. Oh my god, what am I saying, bro? I need to take a nap. Eventual demise of the spotted owl. But that if 50% of the juveniles who survive to leave the nest also find new home ranges, then the population will thrive. Interesting. Again, okay, so the goal of this chapter is to dissect the action of a linear transformation into elements that are easily visualized. All matrices in the chapter are square. The main applications here are to describe discrete dynamical systems, differential equations, and Markov chains. However, the basic concepts, eigenvectors and eigenvalues, are useful throughout pure and applied mathematics. They appear in settings far more general than we consider here. Eigenvalues are also used to study differential equations in continuous dynamical systems. They provide critical information in engineering design as they arise naturally in fields such as physics and chemistry. Okay, all right, let's get to the meat of this subject. All right. Okay. Although a matrix A to AX may move vectors in a variety of directions, it often happens that there are special vectors on which the action of A is quite simple. Okay, let A be the matrix 3 minus 2, 1, 0, and U is minus 1, 1, and V is 2, 1. The images of U and V under multiplication by A are shown in figure 1. Okay, so U goes way down here, but V gets scaled. In fact, AV is just 2V. So A only stretches or dilates V. This section studies questions such as AX is equal to 2X or AX equals minus 4X. Okay, an eigenvector of an n by n matrix A is a non-zero vector such that AX is equal to lambda x for some scalar lambda. A scalar lambda is called an eigenvalue of A if there's a non-trivial solution x of AX equal to lambda x. Such an x is called an eigenvector corresponding to lambda. Note that an eigenvector must be non-zero by definition, but an eigenvalue may be 0. In which case the number 0 is an eigenvalue. Okay. All right. It is easy to determine if a given vector is an eigenvector of a matrix. See example 2. It is also easy to decide if a specified scalar is an eigenvalue. Okay, so let A be 1, 6, 5, 2. U is 6 minus 5. V is 3 minus 2. U and V eigenvectors? Okay, so you just do the matrix vector product and then you factor. So U is and V is not. Thus, U is an eigenvector corresponding to an eigenvalue minus 4, but V is not. Okay, example 3. Show that 7 is an eigenvalue of matrix A in example 2, and find the corresponding eigenvectors. Okay, so you have the scalar 7 is an eigenvalue of A if and only if the equation has a non-trivial solution, so AX equal to 7X. But 1 is equivalent to AX minus 7X equal to 0. Because the thing is subtracting no. This is a vector and this is a vector, so that makes sense. But you can factor out the x and you get A minus 7I times x is equal to 0. To solve this homogeneous equation, form the matrix A minus 7I. Okay, the columns of A minus 7I are obviously linearly independent. Oh, obviously linearly dependent. Yeah, what? So 2 has non-trivial solutions. Thus, 7 is an eigenvalue of A. To find the corresponding eigenvectors, use row operations. Wait, hold on. Oh yeah, that's right. The general solution has the form x2 times 1, 1. Because this is x1 is equal to x2. I think equivalently you could write x1 times 1, 1. Okay. Each vector of this form Okay, warning. Although row reduction was used in example 3 to find eigenvectors, it cannot be used to find eigenvalues. An echelon form of a matrix A usually does not display the eigenvalues of A. The equivalence of equations 1 and 2 obviously holds for any lambda Thus, lambda is an eigenvalue of an n by n matrix if and only if a minus lambda I times x equal to 0 has a non-trivial solution. The set of all solutions of 3 is just the null space of the matrix A minus lambda I. So this set is a subspace of Rn and is called the eigenspace. Right. Okay. The eigenspace consists of the 0 vector and all of the eigenvectors corresponding to lambda. Okay. The set of all solutions of 3 The eigenspace consists of the 0 vector and all the eigenvectors corresponding to lambda. Example 3 shows that the matrix for A in example 2, the eigenspace corresponding to lambda 7 consists of all multiples of this, which is the line through 1, 1, and the origin. For example, you can check that the eigenspace corresponding to lambda equal minus 4. Right, so, okay, so there's really only... Yeah. So, but the thing is, you can't take linear combinations of these, I feel like. Okay, so you take minus 2, you get this, you reduce, then you get 2x is equal to y, so y equals 2x. Yeah, so you get 1/2 1 x2. Oh, I didn't see this 6. Okay. So yeah, so you're gonna get 2x is equal to y minus 6. So then you have 2 free variables and you write it like this. Okay. Okay, so that's interesting that in this case, the dimension of this eigenspace is 2. Right, so the eigenspace is 2-dimensional. Well, that's pretty cool. So there's a whole plane. Remember that once you find a potential eigenvector v, you can easily check your answer. Just find AV and see if it is a multiple of v. Example 4 shows a good method for manual computation of eigenvectors in simple cases when an eigenvalue is known. Using a matrix program and row reduction to find an eigenspace usually works too, but this is not entirely reliable. Round-off error can occasionally lead to a reduced echelon form with the wrong number of pivots. The best computer programs compute approximations for eigenvalues and eigenvectors simultaneously to any desired degree of accuracy for matrices that are not too large. The size of matrices that can be analyzed increases each year. Okay, whatever. The following theorem describes one of the few special cases in which eigenvalues can be found precisely. Calculation of eigenvalues will be discussed in 5.2. The eigenvalues of a triangular matrix are the entries on its main diagonal. The scalar lambda is an eigenvalue of A if and only if the equation A minus lambda I times X is equal to 0 has a non-trivial solution. That is, if and only if the equation has a free variable. Because of the 0 entries in A minus lambda I, it's easy to see that it's a free variable if and only if one of the entries on the diagonal is 0. What does it mean for a matrix A to have an eigenvalue of 0? This happens when AX equals 0x has a non-trivial solution. But 4 is equivalent to AX is equal to 0, which has a non-trivial solution if and only if A is not invertible. Thus, 0 is an eigenvalue of A if and only if A is not invertible. Cool. Okay, yeah, that makes sense. Right, because it's in the null space of A, but the null space of A, if A is invertible, is just the 0 vector or whatever. Yeah, I do exercises at the end. Oh, this document, it's Linear Algebra and its Applications by Lay. You can see it in the title of the video, and I'll put it in the chat just in case. I will be doing the problems. I do pretty much all of the problems, or at least one from every section. But first, we need to read through the section so that it's understandable. Okay, and typically what I'll do is I'll read through the section, then I'll read through all of the problems, and I'll write down which problems I need to do that seem hard, and then I do them. Okay. So that's 0 is an eigenvalue of A, if and only if A is not invertible. The following important theorem will be needed later. Its proof illustrates a typical calculation with eigenvectors. One way to prove the statement, if P then Q, is to show that P in the negation of Q leads to a contradiction. This strategy is used in the proof of the theorem. If V1 to Vr are eigenvectors that correspond to distinct eigenvalues, lambda 1 to lambda r of the n by n matrix A, then the set V1 to Vr is linearly independent. Okay, the proof. So this is theorem 2. Suppose V1 to Vr is linearly dependent. Since V1 is non-zero, oh yes, that's just by the definition of an eigenvector. Back in here, it says, note that an eigenvector must be non-zero. Since V1 is non-zero, theorem 7 in section 1.7 says that at least one of the vectors in the set is a linear combination of the preceding vectors. Let P be the least index such that P plus 1 is a linear combination of the preceding linearly independent vectors. Then there exists scalars C1 to Cp such that the dot product of C and V, Vi, I guess we'll say, is Vp plus 1. Multiplying both sides of 5 by A and using the fact that A Vk is equal to lambda k Vk for each k, we obtain, okay, so this is just, remember, whenever you see something like this, A V equals lambda V, you're talking about the linear transformation is simply scaling that vector. Okay, so we got this identity, then we multiply both sides by A, but then we use linearity and the fact that that they're eigenvectors that correspond to those lambda k's. Then we get C1 lambda 1 all the way, times V1. Okay, multiplying both sides by of 5 by lambda p plus 1 and subtracting the result from 6. Okay, so we get okay. since V1 to VP is linearly independent, the weights in 7 are all 0, right? Because we said V1 to VR is linearly dependent, but then all the ones preceding V plus 1 are independent, just by the, yeah. But none of the factors are 0 because the eigenvalues are distinct. Thus, CI is equal to 0, but then 5 says that VP plus 1 is equal to 0. Oh, right. Which is impossible. Hence, V1 to VR cannot be linearly dependent. Okay. That makes sense. No problem. All right. Eigenvectors are in difference equation. Oh, wow. This is a short section. Wow. We're already done with it. Okay. Eigenvectors and difference equations. This section concludes by showing how to construct solutions of the first order difference equation discussed in the introductory example. If A is an n by n matrix, then 8 is a recursive description of a sequence xk in Rn. A solution of 8 is an explicit description of xk whose formula for each xk does not depend directly on A or on the preceding terms of the in the sequence other than the initial term x0. The simplest way to build a solution is to take an eigenvector x0 and its corresponding eigenvalue and let xk equal lambda to the k x0. This sequence is a solution because you take a of xk is equal to a times lambda k, x0 is equal to lambda k, ax is equal to lambda k plus 1. Linear combinations of solutions in the form 9 are solutions too. Okay, that sounds interesting. Okay, let's do the practice problems. Is 5 an eigenvalue? The recommended way to check if something is an eigenvalue. Let me think. I think you just have to subtract 5 times the identity and do I minus lambda 5. Let's see, what did it say again? No, yeah, you do. You have to do the row reduction. You do the row reduction of... Okay, so let's just do it. I mean, it's not even that hard. Okay, so we're going to do... Let me just write it down. So A is equal to 6 minus 3, 1, 3, 0, 5, 2, 2, 6. Okay, I'm going to put... Oh, wait, my program closed. Okay, just give me a second to start this up. Okay, so A is equal to 6 minus 3, 1, 3, 0, 5, and 2, 2, 6. So then what we're going to do is A minus 5i. And then we are going to take the ref of this. And actually what I'm going to do is I'm going to say rational. And I think I have to do this dot. Okay, give it a second. It needs to run a bunch of crud. Okay, while we wait for that, let's read the second one. If x is an eigenvector, corresponding to lambda, then what is a to the third x? So we know that ax is equal to lambda x. So then a times x is going to be a times lambda x, which is, so it's going to be lambda cubed x. All right, suppose that b1 and b2 are eigenvectors corresponding to distinct eigenvalues lambda 1 and lambda 2 respectively, and suppose that B3 and B4 are linearly independent eigenvectors corresponding to a third distinct eigenvalue lambda 3. Does it necessarily follow that B1 to B4 is linearly independent set? That one's interesting. I need to get some water. What is RF? Reduced row echelon form. Okay, so what this shows is, oops, that's not what I wanted to do. So this matrix oh, you know what it is? Okay, so if we do the reduced row echelon form and we find that it's a diagonal matrix, it's full rank, then 5 was not an eigenvalue because you need to have a free variable. You need to have a non-trivial null space of what's called the eigenspace. But if the eigenspace is just the 0, then it's not going to be so for 1, it's no, 5 is not an eigenvalue of A. Okay, 2. If x is an eigenvector of A corresponding to lambda, what is A cubed x? It's just going to be lambda cubed x. Okay, problem 3. Suppose that B1 and B2 are eigenvector. Yeah, we just read this. Is it possible to have an eigenvalue, two distinct eigenvectors for the same eigenvalue that is not a scalar? I actually think that that's consider the equation. And I think you can't have if you can't have two eigenvectors that are dependent, i.e. scalar multiples of each other, such that they have different eigenvalues. Meaning you have to scale up by the same amount if it's on the same line. So, okay, but however, I'm trying to think about a space that, like, let's say that we had like 2 on the diagonal. Okay, I don't know if there's an operation such as eigen. Okay, so if A was just 2i, like this, then the eigenvalues. Okay, so in this case, we found a matrix A such that we have a non-distinct eigenvalue, but linearly independent. So that would correspond to this B3 and B4, for instance. Okay, so if we take C1 B1 plus C2 B2 plus C3 B3 plus C4 B4 equal to 0, and then we apply A to both sides, then we're going to get C1 lambda 1 B1 plus C2 lambda 2 B2 plus lambda C3 lambda 3 B3 plus C4 lambda 3 B4. Okay, so I don't know why considering this equation actually gives us anything. So lambda 1, lambda 2, and lambda 3 are all distinct. I think it is linearly independent. I was kind of leaning towards it not being, but I think it is. But I couldn't say why. Okay, here's why. So I think if you have two distinct eigenvalues, then the corresponding eigenvectors must be independent. So then B1 and B2 are independent, and both of those are also independent of B3 and B4, and B3 and B4 are independent. Okay, so I'm going to say yes for 4, or for 3. All right, problem 4. If A is an n by n, we are going to look at the answer to this because I don't really quite understand that. If A is an n by n matrix and lambda is an eigenvalue of A, show that 2 lambda is an eigenvalue of 2A. Okay, so I think that one's pretty straightforward because if you have 2A, all right, wait, let's just say that we have A minus lambda I x is equal to 0 for x not equal to 0. Then and then if we multiply 2A, how do you show that? We'll go get a sweatshirt. I'll be right back. Okay. So what are we trying to prove? We're trying to prove that if we know A is if we know that A has a lambda as an eigenvalue, then 2 lambda is an eigenvalue of 2A. Okay. I think that one's actually way easier than I think. Okay, if you know that A minus lam times I times x is equal to 0, then if you do 2 times A minus lam I times x equal to 0, because then you're going to get 2A minus 2 lam times I. So I think that that's the whole thing. Can you actually do this? Wait, do we have A? A minus I. Let's just say x equals rand 2. Oh yeah, cool. You can juxtapose like that. That's nice. That makes the syntax kind of clean. All right, so let's see how they... Oh man, for a 2-page section, they got 50 problems. Okay, so they start doing the row reduction for 1. At this point, it is clear that the modulus system has no free variables. Thus, it's invertible, which means that 5 is not an eigenvalue. Right. Because you got to think about it geometrically. You got to think about you're subtracting this value and in some way you're collapsing down the dimension. And why is it that if you collapse down the dimension, that you can get a vector that it scales by that amount? Okay, so here we got lambda cubed x, and then yes, suppose that since any linear combination of eigenvectors corresponding to the same eigenvalue is in the eigenspace for that C3 plus C3b3 plus C4b4 is either 0 or an eigenvector of lambda 3. If this were an eigenvector of lambda 3, then by theorem 2 would be a linearly independent set, which would force C1 equal to C2 is 0. What did theorem 2 state? Oh, yeah, right. Theorem 2 says if you have eigenvectors corresponding to distinct... Right. Okay, so... Okay, cool. Oh yeah, that's easy. That's the easiest way to do it. I don't know why I did it my way. Sometimes you got to do it the stupid way. Yo, what's up, Kvids? All right, so let's read through all the problems. Okay, good. It looks like a lot of busy work. All right, so 1 through 8 is all just test if something is either an eigenvalue or an eigenvector. So we'll probably just do that in with a calculator. Okay, then find a basis for the eigenspace. Okay, so I'm probably going to do, all right, so let's just do the odds here. So let's do 1, 3, 5, 7, 9, 11, 13, 15. All right, so 1 through 15 odd. All right, find the eigenvalues of the matrices. All right, we'll do 17. 19. With no calculation, find an eigenvalue. I don't know how you're supposed to do 19. All right, we always do the true false. 21 through 30. All right. Explain why a 2 by 2 matrix can have at most 2 distinct eigenvalues. Explain why an n by n matrix can have at most okay, we're definitely doing that. And I think the reason is I mean, one argument that you can make is let's just take an arbitrary diagonal matrix A with like x and y on the diagonal and zeros elsewhere. Then the eigenvalues are going to be x and y. And if you look at the dimension of those eigenspaces, you're going to get if you sum the dimension of each eigenspace, you're going to get. Actually, is that like stupid? Maybe that's a dumb argument. All right, we'll get to it. Construct an example of a 2 by 2 matrix with only one distinct eigenvalue. We could do that. Seems pretty easy. I'm just gonna pick the identity matrix. There we go. We already did it. The identity matrix. All right, 33. Let lambda be an eigenvalue of an invertible matrix. Ooh, that one's cool. That's really cool. Yeah, we're doing that one. So I mean, that one should be easy, right? If you have ax equals lambda x, and then you left multiply A inverse, and you get x is equal to A inverse lambda x. Then that's going to be equal to x times lambda times A inverse x. And then you divide by lambda on both sides, and you get 1 over lambda x is equal to A inverse x. Interesting. I didn't even think about that. All right, 33. I just did it, but I'm going to do it, with my camera on the paper and whatnot. 34. Show that if A squared is the zero matrix, then the only eigenvalue of A is 0. Show if A squared is the zero matrix. All right, that one seems good. I don't immediately see how to do that. 35. Show that lambda is an eigenvalue of A if and only if lambda is an eigenvalue of A transpose. Yeah, we'll do that. Let me think about that though. We assume that A is square, right? Does it matter? Yeah, we assume that A is square, right? Yeah, I think we can assume A is square. For any square matrix, the determinant of the transpose is equal to the determinant of A. So therefore, I mean, we're kind of using stuff that we don't know yet, but the characteristic polynomial is going to be the same. That being said, okay. Use exercise 35 to complete the proof of theorem 1 for the case when A is lower triangular. Okay, maybe. 37. Consider an n by n matrix A with the property that the row. Whoa, that's kind of weird. Consider an n by n matrix with the property that the row sums all equal the same number S. Show that S is an eigenvalue of A. Wow, that seems like totally unrelated. That's weird. The row sum. That's weird. 6 is. All right, we definitely got to do that one. That one's crazy, man. 37. 38. Consider n by n matrix with the property that the column sums are all equal. Yeah, that 38 we don't even need to do. Okay, in exercise 39 and 40, let A be a matrix linear transformation T without writing A, find an eigenvalue of A and describe the eigenspace. T is the transformation on R2 that reflects points across some line through the origin. Okay. I get it. That's actually really cool. So the line itself is an eigenvector, and that or is the eigenspace of one of the eigenvectors. Similarly, the arrow from 0 perpendicular to the line through the origin is also an eigenvector. Cool. All right, that's that one. So we'll do 39. 40. The transformation on R3 that rotates points about some line. So the line itself is obviously an eigenvector. But I think that might be it, right? What else could there be? All right, let's do 40. I think it's just the line itself. 41. Let U and V be eigenvectors of a matrix A with corresponding eigenvalues lambda and mu. Let C1, C2 be scalars. Define the linear combination. Okay, so it's like a discrete dynamical system one. All right, we'll do 41. Describe how you might build a solution of a difference equation if you were given the initial x0 and this vector did not happen to be an eigenvector. On what conditions is the direct sum of all the eigenspaces equal to the whole space? I think it's if and only if A is invertible. Oh, really? Oh. Wait. Wait, in the case of this, we have A is diagonalizable. Okay. No, diagonalizable is a totally different thing. But if it is diagonalizable, then the direct sum of the okay, all right, that actually makes sense. Cool. Let me go put some stuff away and get some water. I'll be right back. Okay. Okay, so 42 I do want to do, right? So 42, 43, let u and v be the vectors shown in the figure. And suppose they're eigenvectors. Let T be the transformation for A. Let W equal U plus V. Make a copy of the figure and on the same coordinate system carefully plot out T of U, T of V, and T W. All right, 43 seems pretty cool. I don't really get, I get exactly what TU, TV are going to do, but T of U plus V. Actually, no, you know what? That's obvious because you're just going to get T of U plus V is equal to T of U plus T of V by linearity. And then you're just going to get 2U plus 3V or whatever it is. Yeah, 2U plus 3V. So that's all right. So that one I'm not going to draw the picture, but applying linearity is good. The more that you can apply the linearity, the better, I think. We're going to skip 44. Let's do 47. We'll just do 47 and we'll ask ChatGPT to transcribe this. All right. 1 through 15 odd. Okay, why or why not? 3, 2, 3, 8. Okay, you see how the columns are dependent? Therefore, the determinant of this is 0. 7, 3. So it is. Yes, lambda equal to 2 is. Lambda equal minus 7, 3, 3, 1, minus 1. A is equal to 7, 3, 3 minus 1. A minus A plus 2i. Yes. Yes, it is. And we can just check that with this. All right. To find... Okay, so we're just going to do A is equal to minus 3, 1, minus 3, 8. And then X is equal to 1, 4. Okay, then A times X. And then we can... No, it's not. And we can double check by eigen of A. The vectors... Oh, wait, actually, I don't know. Okay, so we got yes, yes. Oh, wait, why am I doing all the... okay, let's just do 5. Okay, let's just do this. Okay, A is equal to... Which one are we doing? 5. So I'm guessing that I'm not guessing. The eigen, because if you do dot divided by x, you get 0. So the eigen, since they're all equal and they're all 0, then we're going to get the eigen, it is an eigenvector and the eigenvalue is 0. And that corresponds to this one. You see the e minus 16, that's floating point error, but it is. Four, 3 minus. Okay, cool. All right. It's number 7. Do we really want to do this? 3, 0, minus 1, 2, 3, 1, minus 3, 4, 5, a minus 4i. So we have a free variable, so then the eigenvector is going to be so if we have x is equal to minus z and y is equal to minus z, then we're going to have z times minus 1, minus 1, 1. So we have a line, right? So I think, so if we were to get the eigenvector, it should be minus 1, minus 1, 1. Let's just check. There we go. They scale it so that it's normed to 1, but this is the same. I'm sure that if we did, I mean, who am I kidding? I know that it is. What is the matrix again? Oh, I need to do this. Oh, wait, that's not what I wanted. Okay. Yeah, we were doing 7. There we go. Minus 1, minus 1, 1. All right. Enough of that. Number 9. Number 9. Okay, so in this case, we get 6x equals 0, 2x equals 0, x is equal to 0, but y is free. So we get 0, 1 is in, so basis is going to be y times 0, 1. Is y a thing? Okay, so then it's going to be y times 0, 1. That is the basis of the eigen space. Okay, then for 9, we get 2x minus 6y is equal to 0. So we get 1/3, y is equal to 1/3 x. So then if x equals 3, we get 3, 1. Okay, so I would say it's y times 3, 1. I mean, really, it's kind of weird to say y. I don't know what you're supposed to say, but that's what I would say. Okay, let's just double check too. At the end of this book, they have a what were we doing? Which problem? 9. Oh yeah, they just give a vector, which makes sense because you really don't need to have it parameterized by anything. So just 3, 1. Okay. 11. Okay. So see here how the rows and the columns are linearly dependent. So we're gonna get 3x equals minus 3x equals y. So then we get minus 3, or we get 1 minus 3. So how they answered it, they would be 10, 1 minus 3. 1 minus 3. Okay. 13. Do we really want to keep doing all these? All right, we'll do 13. So this one's a little interesting, actually. So we had 3x minus or plus z equals 0, but then we also have minus 2x equal to 0 and minus 2x equal to 0 again. So I think it's, yeah, x is equal to 0 and z is equal to 0, but y is free. So we have just 0, 1, 0 corresponding to lambda equal to 1. Then we do 2, and we get, so then lambda equal to 2, we get x is equal to minus 1/2 z, and y is equal to z, with z free. So we get z times minus 1/2, 1 and 1. Okay, so this one was 0, 1, 0. This one is minus 1/2, 1, 1. And then the last one is minus 3i. And we get, so for lambda equal to 3, we get x is equal to minus z. And we get y is equal to z. So then we're going to get, is that the same one? We're going to get minus 1, 1, 1. Okay. This one I did wrong. Wait. Oh, wait. No, wait. I got it right. Yeah, I was like so confused for a second. No, but that's right. Cool. All right. So we don't need to do problem 15. We've done enough of these. I was kind of hoping for one of them to have a basis, a two-dimensional basis. But you know, whatever. Wait, 17. Okay, so here the eigenvalues are going to be 0, 2, and -1 because it's, notice that it's upper triangular. Similarly, this is lower triangular, so it's going to be 8, 0, and -4. Now for this one with no calculation, see, this is the one that I didn't know how to do. I mean, so for any vector that you give it, it's going to end up being 3 copies of x plus 2y plus 3z, right? But I don't know if that tells us how to find for A, find one eigenvalue with no calculation. Okay, I'm going to ask. I don't know how to do this one. File upload pending. What the? Okay, so they're all, yeah. The rows are identical. If you have two identical rows, then the determinant is 0. Oh yeah, that's what it is. If A is not invertible, then 0 is an eigenvalue, right? By, what was the theorem or something like that? Where did it say that? What does it mean? Right. Right. Damn. So that means that, so if you recognize that thus 0 is an eigenvalue of A if and only if A is not invertible. So this A is not going to be invertible because it has linearly dependent columns. So 0 is not, so 0. Okay, 20, it's the same, it's 0. And then find the two eigenvectors. So for this one, 101 and, or yeah, 101 and maybe -1, 0, -1. Wait, but those aren't independent. Oh, here's what you do. You do, for 20, you do 101 and 011. Those are independent. So let me just test that out. So if we have A is equal to 4, 4, minus 4, 4, 4, minus 4, and 4. Oh my god. Why is Copilot making me... Okay, so that's so stupid. There's no just solve. You really got to write A backslash zeros 3. It's so silly. Anyways, what am I trying to find? I'm just trying to find A times 1, 0, 1. Oh, I could also do null space of A. Wait, so is this 0? And then this should also be 0. Okay, cool. So we found two independent vectors that are without calculus. We really didn't do any calculus. We just did checks. All right, let's go. True, false. You know I love true, false. A is n by n. If ax equal lambda x for some vector x, then lambda is an eigenvalue. So I'm going to say false because it didn't specify that x is non-zero. If should I say false again? I think I need to say false again. A is invertible if and only if. No, it's false. So A is invertible if and only if 0 is 0 is an eigenvalue if and only if A is not invertible. Okay. A number C is an eigenvalue of A if and only if the equation has a non-trivial solution. That's true. Finding an eigenvector of A may be difficult, but checking whether it is easy. Yeah, that's true. 26. To find the eigenvalues of A, reduced echelon form. False. If V1 and V2 are linearly independent vectors, that's not true. That's not necessarily true. You can have linearly independent eigenvectors that correspond to the same eigenvalue. Just consider the identity matrix. I wonder what happens if we can do. I bet this fails. Eigen of I. I actually wonder if we. What happens if we do? No, but I think that this also fails. Eigensystem of identity matrix. This probably just returns itself. You have to go. But that's boring. But anyways, look at the vectors are independent, but the there's multiplicity in the values. So oh, this is the wrong thing. So so 27 is false. 28. The eigenvalues of a matrix are on its main diagonal. That's false. It's only if it's triangular. If V is an eigenvector with eigenvalue 2, then 2V is an eigenvalue vector with eigenvalue 4. So okay, so we have AV is equal to lambda V or 2V. This is a good trick question because that's false. 2V is an eigenvector with eigenvalue 2. It's because it's the same thing. So it's only they try to trick you from earlier, but that's false. That's totally false, man. An eigenspace of A is a null space of a certain. That's true. That's true. I mean, it's kind of a weird way to say it, but I would say that's true. All right, we're just going to check our answers. Right, non-zero, non-zero. Okay, so false, false, false. True, true, false. True, true, false. I hate that they renumber these. It's like I gave you the actual numbers. Why would you renumber them? It's so confusing. 27. It's like so annoying. It's like I don't know why they would think to renumber them. Okay, 27 is false, 28 is false, 29 is false, and 30 is true. All right, good. Okay, wait, what other problems did we have to do? Okay, so we just finished 30. Now we have 31 through 35. Let me just write them down here. Did I write them down? I don't think I wrote them down. All right, let's just do 31 through 35, 37, 39, 40 through 43, and 47. Were there any ones I was even excited about? Oh yeah, these were the ones I was excited about. This one I was trying to make an argument about the dimension of the eigenspaces or something like that. This one was the identity. Let me get some water. It's good stuff. Okay, so I want to know the answer to 30 really bad. Or 32, 31. Okay, suppose that the 2 by 2 matrix had 3 distinct eigenvalues. Well, then by theorem 2, this set is linearly independent. However, it's impossible to have 3 independent vectors for a 2-dimensional space. So the contradiction, therefore, but the thing is, I feel like that's not the proof that I wanted. I feel like I wanted a proof that's deeper than that. So what does it mean? We have 3 values. Okay, wait, what was the proof of theorem 2? Weird. Bro. I mean, got to, man. Mongolian, dude, that's so sick. That's awesome. Look at these sick pages. Dude, I love ancient math. Ming. Bro, Mongolian script is so cool too. Oh, this isn't an image. This is real text. That's so cool. I love that they write top to bottom, dude. So freaking cool, man. Mongolian is dope. All right, I'm not gonna go on this whole thing about. Yeah, yeah, I bet almost all are OSs. That's funny. I mean, it's yeah, that's funny. What the hell, bro? I'm bleeding. I think it's just a hangnail, but I'm bleeding a lot. Damn. All right, whatever. All right, why am I reading about Genghis Khan, bro? I got homework. Freaking Genghis Khan. All right. Anyways, that's really cool. Um, all right, let's just keep going. Right? Let's just keep going. We did 32, 31. All right, this one was easy. So you just let. Okay, so let's just say L is lambda. Then we have AX equals LA. Then we multiply. Then we left mul A inv A. Then we get X is equal to, or wait, let's say inv A X equal to inv A LA is equal to X is equal to inv A LA, which is equal to X is equal to L times inv A. Wait, this is supposed to be an X, right? It's supposed to be an X. Okay. Then we get inv x is equal to inv ax. Wow, Copilot is really bad. I don't know how it keeps messing up. All right, but that's pretty sweet. So then that shows that therefore invel eigenval of inv. Okay, we did it. Now this one seemed weird. Well, I was just sitting down and then I felt this like sticky wet stuff. I knew it was blood. Sometimes you could just tell it feels like blood. Wait, which problems do we have to do? Let's just keep going. A squared equals 0. Show 0 only eigenval of A. How do you do that? There's some weird stuff about. There was a problem earlier about powers of A equaling 0. I forget what it was though. If because I know that's wrong. But why? Oh yeah, because A is not invertible. You can't do that. Right. So you definitely can't do that. But I'm stuck. So if A squared is the 0 matrix, then the only eigenvalue of A is 0. Okay, wait. Okay, so you have A squared V is equal to 0 because A times AV, but we assume lambda not equal to 0. So then we get a times lambda v is equal to 0, which is equal to lambda a v is equal to 0, means lambda squared v is equal to 0, but lambda squared. But since v non-zero, by definition of Eigenvec, then lambda is equal to 0. Okay, that's chill. I'm down with that. How long have I been live for? Well, I just went live an hour and 40 minutes ago. I took a break to eat. All right. So we just did 33, 34, 35. Show that lambda is an eigenvalue if and only if. Okay, so for 35, we want to show that that AV equals lambda V implies A transpose V is equal to lambda V and vice versa. So this is the if and only if. So if we go this way, how do you show this? Okay, first find out how A minus lambda I are related. Okay, well, I guess the thing to note is that A minus lambda I transpose is going to be equal to A transpose minus lambda I. Oh, so I think that's it. So if we have that at A minus lambda I transpose, this prime means transpose in this, is equal to A transpose minus lambda. I don't think you add the second transpose. Because if you transpose it and you subtract it, it should be the same as subtracting it and then transpose it, because the diagonal doesn't change at all. So this gives us this identity. Then wait, let's comment all this crap out. Okay, so since this is the case, and what did we assume? We said assume. So we know that lambda is an eigenvalue of A transpose. So that means that this has a non-trivial vector equaling okay. For some non-zero v. Now we want to use that to imply oh wait, no. This is 0. I'm sorry, I'm messing this up. Anyway, so but this is the same as A transpose V is equal to lambda V, right? So that's the same. All right, I think it all just depends on this identity, but I'll let's see how they are supposed to do it. Okay, so this is the identity that I came up with. Okay, so that's how they show. They just show it using determinants. That's fine. I'm down with that. This is the one that I wanted to do. 37 is wonky, man. Because the weird, I guess the simplest. Because what I came up with was this weird. Where was that one? 2, 1, 3, 1, 2, 3. This one. This one was really interesting because. So if you look at the rank of A, then you get 3. So this is an independent. This is invertible. You can take inv of A. But the cool part is that sum each. You can't do that. Anyways, they're all 6, right? So S is 6. And if you look at the eigen of A, 6 is one of the eigenvectors or eigenvalues. But why? Why, dude? Why is that the case? That's so ridiculous. How do you prove that? The hint is find an eigenvector. Okay, fine. We'll find an eigenvector. So let's just say, let's just say A minus 6I. Or wait, can we do a 2 by 2 actually? Let's do a 2 by 2. Okay. So we're going to get 4 minus 4. Oh. Wait, no, is this just a coincidence? I feel like that's just a coincidence. Yeah, because I could do... Yeah, so it's not that it's symmetric or anything weird like that. Wait, but it doesn't even have to be that they're the same numbers. We could just do like 3 and 0. Okay, so what we're trying to find now is that we're trying to find the null space of this. That doesn't tell me anything. I really don't even know what that means. -1, -1. I mean, okay, what does it really mean? It means that all of the rows Let's look at the eigen of this one again. So that's definitely a clue, right? I mean, if we took like 10i eigen 10i 3. That's a bad example. I don't get it. The eigenvector happens to be all equal or something, but like... Oh, okay, that's pretty neat. That's pretty cool. All right. So then 38 is obvious from that, because you just use the fact that transposes have the same... Transpose preserves eigenvalues. But okay, wait. Let's just take let's take rand 3 by 3. Let's just check that its rank is 3. Okay, good. Then eigen of A, eigen A transpose. The values are going to be the same, but the values are the same, but the vectors are not. Okay. We did this one. This is going to be... And then this one, okay, so let's just get the answers, because I say that it's for 39, it's the things along the line of reflection and on the line that's through 0 and perpendicular to the line. And then for 40, I think it's just the line itself. I don't think that there's anything else, because if you're doing a rotation around this R, of R3, what else besides the thing on the line is going to stay? Perfect. That's what I said. And then perfect. All right. That's exactly what I said. Okay, this one I did want to do. I'll probably skip 47. Vector not. But if the matrix is diagonalizable, then is that true? I actually don't know if that's true. Diagonalizable means that there is a basis of Rn consisting of eigenvectors. Or yeah, we didn't have to say Ax, but just the eigen... Yeah, it's an eigenbasis. Bro, the eigenbasis is the coolest basis, man. The eigenbasis is the coolest basis. Let's just be honest. If you have an eigenbasis, either use that or the standard basis. But the eigenbasis rules. That's all I'm going to say. Bro, I just read about this thing called Sperner's theorem. Bro, this theorem rules. The biggest anti-chain is this one. So cool. I mean, I thought you couldn't do better than taking all the individual elements of the power set. But it turns out you can, and you can go way better than that. It's just genius. Sperner's theorem, man. So cool. All right. Let U and V be vectors of a matrix A with corresponding eigenvalues lambda and mu. Let C1 and C2 be scalars. Define X. I think this is going to be K plus 1, right? Okay, I'll do this one on paper. So I'm pretty sure that this is the answer. All right, so for 41, we have x k is equal to C1 lambda to the k u plus C2 mu to the k v. Okay, then we want to say, what is k x k plus 1 by definition? I believe it should be x to the k plus 1 is equal to a of xk, right? And then b is compute axk. Oh, this, yeah. No. So by definition, it's not this. It's that you get C1 lambda k plus 1 u plus C2 mu k plus 1 v. All right. So that's that. So let's just double check, but I'm pretty sure that I got it all. Yeah, so this is A and this is B. Cool. 242. Describe how you might try to build a solution of a difference equation if you were given the initial x0 and this vector did not happen to be an I. How would you relate x0 to the eigenvectors of A? All right, this is gonna be the last one because we already did 43. Go back if you didn't understand that. You just apply t of u plus v is equal to t of u plus t of v, but t of u is, since u is an eigenvector with corresponding eigenvalue 2, you do 2u plus 3v, and then you just draw that. So you go like out here, and it's gonna be like tw is gonna be over here or something like that. So that one's easy, but this one I just want to see the answer of this. Yeah. Oh yeah, primality testing. But this all depends on whether P equals NP, man. So cool. P equals NP. That's just like your opinion, man. Whoa. Oh yeah, right. That's what's so cool is testing whether the matrix mole is equal to a given product is n squared, but matrix multiplication is but that's what's so crazy about that, man. Oh my god. Primality testing, yeah. Yeah, the AKS. Yeah, I've heard of that. But factoring, right? So it's known that primality testing is polynomial, which is crazy that primality testing is polynomial, but factoring is not. If factoring was polynomial, we'd have a big problem. That's so sick. Or yeah, just think about SAT. SAT's a good one. For NP problems, the search version can often be reduced to repeated calls to the decision oracle. Yeah, but it's like it feels so fundamental. Like which problems admit a faster decision. Anyways, it's beyond the scope of this class. Okay, so we're done, right? All right, cool. We'll jump into 5.2 maybe today, probably not today. It's already 4. So maybe we could get one more in. I'm gonna go for a short walk though. All right. Characteristic, we have other stuff to do as well. It's not just linear algebra, but sometimes you just got to do a bunch of linear algebra. Okay. Peace out.